So last Thursday, we already finished until this part. This is the general architecture. If you are going to apply the CNN or the convolution neural network. There's another type of neural network. We call it recurrent neural network. The word recurrent, sometimes they call it RNN. It is a class of neural networks that allow previous output. So this one is the keyword, the previous outputs to be used as inputs while having hidden states. So we will see the architecture about what is the previous outputs. So the advantages of this RNN is the possibility of processing input of any length. It means when you have the input in any length, that it is good. The model size not increasing with the size of input. So no matter the size of the input, the model size will be just stable. The computation takes into account historical information. So if you have t equals to 1, and then you have another data t equals to 2, and then you have another data t equals to 3, and then you want to predict like that t equals to 10. So the historical data will be kept. So you can still remember what you already have in the previous time. And then weights are shared across time. So you have the weight in the time 1, you have the weight in the time 2, you have the weight in the time 3, and so on. So it will be shared all the time. But the drawbacks, the computation being slow. So the RNN usually is not that fast. And then difficulty of accessing information from a long time ago. So if you have only T1, T2, T3 until T10, it is still okay. But if your data from T1 until T, for example, 1000. So if it is too long, then it is difficult to access the information. And it cannot consider any future input for the current state. So it is the drawback, okay, from the RNN. So I just want to explain what are the typical applications for the RNN. If you already learned the neural network, this is the traditional neural network. We have X as the input, and we have the layer or the hidden layer, and we want to predict Y. So we can have a kind of coefficient or bias. So in this case, we have the Tx. It is, let's say we have one kind of variable, and then we have one class or one type of prediction. So we can say this is 1-to-1. So the traditional network that you learned before is typically like this one. But there might be another kind of application, for example, music generation. Let's say I want to give input a kind of music. Let's say the X equals to jazz. I want to have a music. I want to have a jazz music. Then this layer will learn something to give some bits of the melody. So maybe this is the first melody, this is the second melody, this is the third melody. So this kind of music generation, we can use RNN. Sentiment classification. If you know sentiment classification, we want to find out whether a text is good or not, whether a text is positive or negative. For example, I love bulgogi. Then the sentiment, we know that the word love is positive. So we can have like the result is positive. So in this case, I have several input x1, x2 until xtx. So I have the word I love bulgogi. But the prediction is only one. I know that it is positive. Yeah, usually we use this one for the review, or if you do with the online shopping, or if you book hotel or travel, you have this kind of review, then yeah, you can use like this kind of RNN. Name entity recognition. We have many to many. So we have many words in an article, and then we can predict what is the meaning by that word. I don't have the information. Maybe I can just show you. So name entity recognition. So in Python, they already have the library. For example, like this one. I have this text word. So when we have a name, this is the name, then the RNN can understand that this is an organization, ORG. ORG means organization. And then by FBI agent, okay, maybe this is difficult to predict because it is attached to the word by. And then Peter Strokes, okay, the library can indicate that this is a person. Okay, who criticized Trump? Okay, this is person. Okay, and then FBI. Okay, this is a kind of organization, or this is the government, yeah, government entity. And then yeah, Trump. This is a person. This is a person. Okay, and then this is an organization, and so on. So we can know for every of this name whether it is representing person, or it is representing an organization, or it is representing a government entity. So we call this is the name entity recognition. And we can use this with the RNN. Or we can also do with the many to many. We call it this is many to many, such as the machine translation. So if you use like Papago, or you can use the Google translation. So that kind of example will be the machine translation. So if I have a word, I will go to school tomorrow. Then yeah, this is word by word. The word I will go to school tomorrow, and then we can go to this kind of layer to have a translation to Korean. 학교 내일 학교 가겠습니다. Oh, yeah. That will be the word in Y. So using the recurrent neural network, usually we can have the like word or music or yeah, text or time series data. So in the RNN, there is another variant. We call it the GRU and also LSTM. This is just an introduction. Okay. So the GRU is gated recurrent unit, and the LSTM is the long short-term memory units. It is to deal with the vanishing gradient problem. Do you still remember this one? Vanishing gradient problem. So I will show you again another picture to show about this vanishing gradient problem. So this vanishing gradient problem, it is encountered by the traditional RNN. If you use the common neural network, if you want to deal with this vanishing gradient problem, you can use the activation function. One of the activation function that you learn is the sigmoid. In RNN, there's also a problem with this vanishing gradient problem. So the traditional RNN can be improved by the LSTM, and it can be improved also with the GRU. So this is the architecture of the GRU. I think it's not that easy to understand in very short time. So I will just give you introduction about this architecture. Okay. So the important point is this part. This part. So what are they? Actually, I put this one. This is the type of gates. Sorry, let me jump a little bit. So the first is, we call it the update gate. We have also another gate, we call it relevant gate. And we can also see another gate, we call it forget gate and output gate. So the GRU and LSTM, they have the update gate and the relevance gate. It means they will check whenever they have the hidden layer, they will just took the relevance information and then they will update it. So the rule is how much pass should matter now, and then should I drop the previous information. So there is GRU and LSTM, they use this gate. For the LSTM, they have another gate, they call it the forget gate and the output gate. So the forget gate means I will erase which information that is not important. And then the output gate, how much to reveal of the cell. So if you look at the architecture, we have U, which is update, we have R, which is the relevance. But in the LSTM, we have F. So some of what we are learning before, we can forget it. So if it is not important, it will be removed. If it is important, then we will update it. And then after we update it, we can find the relevance. And if it is relevance, then we will put it as the output. So that's the mechanism in the LSTM. In the GRU, they just have only two gates. So whenever we have the vanishing gradient problem, so this is one example of the unstable behavior that you may encounter when training a deep neural network. So if you don't have any activation function, then it will give you some kind of decreasing like this one. So if it is nearby 0, then if the neural network has many hidden layers, so if there are many hidden layers, there are many hidden layers. If there are many hidden layers, it is good because they can predict more, they can predict a better way. But the problem is the gradient in the early layers will become very low as we multiply the derivative of its layer. As a result, learning in the early layers becomes very slow. And if it is getting long, if getting slow, then maybe it will give you 0. So that's why we need the activation function in order to activate a bigger number. So this is the way of the activation function works in the traditional deep neural network. So the same idea, if we use the sigmoid function, I think if you still remember the sigmoid function, the sigmoid function have this kind of pattern. When you do the sigmoid function, then the number that will be delivered to the next layer will increase as follows as this function. But there is another activation function, we call it ReLU. So the derivative of the ReLU function is either 0 or 1. So in the ReLU, the derivative will be either 0 or 1. So this will be also a problem when we use it in the neural network. So the error signal is also dependent on the weights of the network. If you still remember the weights when we learn about the neural network, it will be depending on the weights. If the weights of the networks are constantly below 0, then the gradients will diminish slowly. So if it is below 0, then it will degrade slowly. So there's another option. We can use the leaky ReLU in order to improve this kind of activation. So this kind of activation function is really depending on your data, what kind of data, and yeah, we need to do more experiments. What is the best activation function for your data? Okay, so this is the type of kits that I mentioned before. It is to remedy the vanishing gradient problem. So the specific kits in the RNN, it will be useful to overcome the vanishing gradient problem. Yeah, that's the introduction of the deep learning. So the last part in the deep learning, I want to explain about the performance measures. How we can measure the performance of the deep learning. So the performance of deep learning depends on the parameter setting. Last time we learned about the batch size, and then we learned about the epochs. Optimizer, if you use orange, you can see some of the optimizers, like the Adam optimizers or some other optimizers. Loss function. Because you already learned this one, yeah, you can look at the materials before. So today we will learn the optimizer and loss function shortly. For optimizing the parameter, it tends to use the hyperparameter tuning. So this task is common. We need to tune. Tune means we need to find a good number. we need to find what is the best number. So I will just explain the basic one. The basic optimizer is the gradient descent. And there is another variant, we call it the stochastic gradient descent, mini batch. Other kind of optimizer, we call it the adaptive gradient algorithm, ada delta, ada optimizer, and etc. So let's see just the gradient descent. So in the gradient descent, there are three types of gradient descent. The gradient descent uses the whole training data to update weight and bias. Suppose if we have millions of records, then training becomes slow and computationally very expensive. So if we have the whole training data, of course it will be very slow. There is another update, we call it SGD. SGD, it is the, I didn't put this one, stochastic gradient descent. The SGD is the stochastic gradient descent. So it tries to use only single record. So if we have a lot of data, it uses the single record to update the parameters. But still SGD is slow to converge because it needs forward and backward propagation. It is for every record. And the path to reach the global minimum becomes very noisy. If you look at the graph here, the gradient descent is very smooth to find the optimum loss, but the stochastic gradient descent, it is very noisy, so it will be fluctuated, and it is difficult to find the global optimum because of this noisy. We have another approach, we call it mini batch gradient descent. It overcomes the SDG drawbacks by using a batch of records to update the parameter. So if the SGD will use 1, 1, 1, 1, so every single record to update the parameters, but the mini batch gradient descent, they will use the mini batch like this one. Maybe I will like to use 4 pages. Then I will use 1, 2, 3, 4 as one set to update the parameters. Since it does not use entire records to update parameter, the path to reach global minimum is not as smooth as gradient descent. So this is the result from the mini batch gradient descent. Even though it is not that noisy like SGD, but yeah, it is still have some fluctuation, and the result is it's quite good. It is to overcome the problem in the gradient descent, and it is to overcome the problem in the SGD. So nowadays people try to use the mini batch gradient descent to make the performance better. If we look at the loss function, there are some performance metrics. If it is about regression, you already know the mean square error. Okay. So we have the prediction y I, let's say, minus by the actual of yi. So the example, you can see it from the moving average example in the time series. Yeah, we will use this equation, and then because it is square error, so you will make it as square, and then you will do the summation and divide it by the total data. For the binary classification, they have the binary or cross entropy loss, and for the multi-class classification, we can use the categorical cross entropy loss. We call binary cross entropy. It is to compare each of the predicted probabilities to actual class output, which can be either 0 or 1. And then it will calculate the score that penalizes the probabilities based on the distance from the expected value. That means how close or far from the actual value. So if you're dealing with the multi-class classification problem, you can calculate the log loss in the same way. So let me just give you one example. It is better to show with example. So the binary cross entropy is the negative average of the log of the corrected predicted probabilities. Let's say like this. I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 data. The predicted probabilities. What is it? This is I think, oh, my typo here. The output is given. Okay. So the output is given by the model that tells the probability object belongs to class 1. Okay. So you need to know this one, or you need to give this assumption, or you need to set this kind of modeling at the first time. So if this one actual is 1, okay, then the predicted probability and the corrected probability is the same. So let's say I have this actual 1 and the predicted probability is 0.94. Then I know that the probabilities of this prediction is giving a high probability to the class 1. So I can create the corrected probabilities. The column corrected probabilities is the same with the predicted probabilities. Now let's see if this is ID6, ID1 is also the same. It is actual 1. ID7, it is also the same. It is the actual is 1. But what about the ID8? The ID8, the actual is 0. Okay. What is the predicted probabilities? The predicted probability is about the output, and the probability object belongs to class 1. So this is 0.56 is the predicted probabilities that belong to the class 1. However, the actual is 0. So we need to correct the probabilities. How to correct it is we can just do the subtraction. 1 minus 0.56. then the result is 0.44. Okay. Let's see another example. ID2. The actual is 0. Okay. The predicted probability is 0.51. And we know that this predicted probabilities is the probability object belongs to class 1. Then we need to correct the probabilities because the actual is 0. So this will be corrected by 1 minus 0.51 and the result will be 0.49 and this number will be in the corrected probability. So if it is 0, 0, 0, then we need to put the corrected probabilities. Okay. Now, after we have the corrected probabilities, we need to make it as a log. I think you learned last time, we learned about the neural network. Okay. One of the performance measures is the log loss. So the log value offers less penalty for small differences between the predicted probability and the corrected probabilities. So it will check the difference, okay? It will check the difference between the predicted probabilities and the corrected probabilities. Okay? So when the difference is large, the penalty will be higher. So if we have this number, okay, actually 0.94. So it is nearby 1 or 0.90. It is nearby 1 or not. This nearby 1 or not. So if it is far or if it is large, then the penalty will be higher. So you can make log of 0.94. Let's see. Let me open the calculator. Zero point 0.94, and then I will put log. Okay, so you can get the value minus 0.028 something. Okay. Let's see, 0.9. So 0.9 log. Then you can get the 0.0457 something. Okay. Now the formula is log pi. Okay. We have the minus something. We have minus something, and then we need to do the summation. Okay. We need to do the summation and then multiply by minus 1 divided by n. Okay. N is the number of the data. So let's see. The value of the negative average of corrected probabilities we calculate comes to be 0.214, which is our log loss or binary cross entropy for this particular example. So how can we get this number? 0.214. So we need to calculate for every of this log number. Okay, let's say I remove the minus because at the end you need to multiply with minus 1. So I can just calculate with 0.0268 plus 0.0457 plus 0.1079 plus 0.3565 plus 0.3098 plus 0.3279 plus 0.4948 plus 0.0457. Okay. Okay, the result is, yeah, okay. Whenever you do with this calculation, I guess there might be some, yeah, if you forgot to put the comma, some values, maybe because I put some of the values only 3 digits after the comma, then it will be like this one. So 1.7151. And then we have how many data? 1, 2, 3, 4, 5, 6, 7, 8. Okay, we have 8 data. Then we can divide by 8. Okay, the result will be 0.2143875 something. So we can say that the log loss for this problem is 0.214. Okay. What about if we have multi-class classification? So we have the yi is the actual, and then we will multiply with the probability. Okay. The probability is the same like this one, the corrected probabilities, and then we will check what is the other class, and then we will multiply with log 1 minus the probability. You can also use this way for the log loss of multi-class classification. We have Yij log Pij. And then we will do the accumulation for all the rows, and we will do the accumulation for every of the classes. Yeah. So please try to review this one. I think there will be one problem about this in the final exam. Okay, so at the end, I think we finish everything about this data mining class. So what is the trend of this data mining? People now comes with a new word like data science or the machine learning. So the trend in the healthcare industries, they will just say not about the data mining again, but it is more bigger. Or we can say it is broader, like data science, data analytics. They represent almost the same with the data mining. So for example, this is the example from the Samsung SDS. They have the Predix AI. Okay? So they want to create the automation in the data mining. So what you did now with Orange, it is a kind of automation because you can create the workflow. Okay? So you can create the workflow, and then you can do something. After you have the workflow, what is the result at the end? So in this Predix AI, they have the process. This is the process in the company, and then based on this process, they can do automation in the data mining for every of this process, or they can embed data mining in every of this particular task. And there are many trends nowadays. If you are working on the spatial and the geographical data, it is also now a trend because the global warming issues, or if you are working with the satellite and the Internet of vehicles. Now there are many automated vehicles, so they are working on this geographical data mining. And you learn one kind of tools from the Python, which is the orange. But actually, yeah, I think in the future, all the tools can be consolidated. The orange data mining is based on the Python. There might be another tool, Rapid Miner. This Rapid Miner is based on Java, but now it can be connected with Python. Anime is based on Java. So if you learn Solver, Solver in Excel, they also try to develop the data mining for the Excel data, and so on. So those data mining tools are available, and yeah, it will be depending whether you are going to use the simple workflow like Orange, or you are going to use the Python with the script, or any other tools like SAS, or we have the Oracle Business Intelligence, which you have to pay some money. Okay, I think that's all what you can learn until this semester. Okay. So you already learned many things from the basic machine learning until the deep learning. And I give you example if you want to try with the regression or the classification using the deep learning. I give it in the Google Colab. So the first is about the regression with the simple yeah, I use this with the LSTM network again. So you can take a look how if you want to use Python to do with the LSTM for this data set. This is a data from GitHub about the airline passengers. So we want to predict if we have the data in this year 112, we have this data in this year 118. So if we want to predict what will be the data in the next year, so we can use the regression. In this case, this is the way. Okay. And there's another data that I'm using this one for the classification. Yeah, if you want to look at the details, you can look at this deep learning with the keras. Okay. So this is an example with the CNN. Okay. So you can see this is using the activation value, and we are using the max pooling. So this is the architecture that you learn in the basic deep learning. Okay.